Hey everybody, welcome back. I'm glad to finally see you again after a little hiatus. I hope you've been enjoying the lectures by somebody else other than me. Andrew's got a really nice kind of vibe, I think, in how he handles the math. So I think you probably were in better hands than if I had done it. However, I do want to give you some Python version of all the support vector machine stuff we've been talking about, or you and Andrew have been talking about. So without too much further ado, here is a little notebook, which I'm going to run through with you, but you will, of course, have it available for your own downloading. You can open it up on Google Colab or your own machine or whatever works best for you and play around with it. And I suggest you do because you get a chance to understand a little bit more about the parameters and the ways in which support vector machines function. Okay, well, let's get into it, right? So as usual, we need to generate some fake data. That is always step number one. So let's make something with two blobs, which are very clearly separable. Okay, so if you look at these two blue and orange blobs, you can very much imagine you could create a discrimination function, a line that would go between them and separate them. But as always, right, there's more than one possible line that can do that. So for instance, here are three different lines that can take a separation and definitely label orange class from blue class with 100% accuracy in this training set. However, yeah, that's training set. If we get a new sample of data marked with that red X, which class is it going to be in? The negative class blue or the positive class in the orange? Well, it depends on where you draw that line. And obviously with multiple different lines that can be drawn, which one is the right one? So the intuition, as you've seen already in the lectures, is that the best possible line, in one sense of best possible, is to draw the line that maximizes this margin, the space between the two blobs. So you want to have just as much space above the line as you do below the line in a way which makes sure that the line gives you the best possible space in between the blue and the red, or blue and the orange. Okay. So what does that mean? So we're going to draw the line which goes through the middle between those two, right? So so the middle is a bit deceiving, right? Because if we draw this line here, right, then we are saying explicitly that this line, this distance from the blue dot to the black line is the margin. And over here, it's from the orange dot to that black line there. And that distance, that perpendicular projection that we saw in the lectures, is the margin, right? It's one side of the margin. And the two sides of the gray there together are the full margin. So this is saying that the distance perpendicular to our discrimination line is this small amount, the gray on both sides of the function. Okay, and likewise, if we draw this line here, then we end up with the same problem, right? Where we have a relatively narrow band between orange over here to the black and blue over here to the black. However, if we draw a line through the middle here, then this is the closest element, that blue again, and we get a much bigger margin on that side. And over here, like this is one of the closest, and that is a much bigger margin on that side. The margins are the same on each side, right? The line goes through the middle. And that's definitional by the fact that we have that, +1 and -1 in both the loss function and in the definition of where these margin lines go. This is y is equal to mx plus b equals 0, right? So this is the weight vector times x plus b equals 0. And this one over here is wx plus b equals to -1. And over here, it's mx plus b, or wx plus b, sorry, equals to +1. So definitionally, these two are 1 apart as scaled by the weight vector, okay? So whatever the scaling of the weight vector is, that defines what this distance is, right? How big that margin is. And we saw that again in the lectures, right? That the norm of the weight vector is what's being minimized by a support vector machine. And the denominator of the norm is the divided by the norm of the weight vector, tells you how big the margins are there, okay? Because they're scaled by the weight vector. All right. Again, sorry if that doesn't quite make a whole lot of sense the way I'm telling it, because I'm assuming that you've all seen these lectures already, which go into this in great detail. All right, so let's get on with the demo, because what support vector machines do is they choose the line that gives you the maximum margin, which is a function of where the line is or in the space and the size of those weight vectors. All right, so to get the job done, we need to use the Scikit-Learn library for support vector machines, okay? So in this case, we're going to use the SVC, which is a support vector classifier. Just so you know, although we're not addressing it at all here, you can use this same math to do a regression instead of a classification, okay? Where you can use the support vectors to find out where to predict a real number for whatever, right? Whatever output variable you want to predict, that's a real number instead of just a class. So we're not going into that, but the SVC is the support vector classifier in Scikit-Learn, and the SVR, support vector regression, is a different function. Now, why are we going to use a library like Scikit instead of just doing the math ourselves like we did with OLS? Well, as you heard in Andrew's last lecture, there is a real clear, there's a lot of computational tricks that are done with support vectors. To make them work at all requires quite a lot of engineering of the mathematics of calculating the answer. And to make them work well requires even more tricks. So it's kind of beyond the scope of this sort of class about how to program a support vector implementation. And in fact, as far as I know, almost everybody who does this kind of work uses actually the exact same library. There is a reference standard library written in C, which is used, in fact, by Scikit-Learn. So Scikit-Learn just throws Python wrappers around this C library. And I don't know of an implementation that doesn't use this exact same C library. Okay, so there you go. So we're not going to reinvent the wheel. We're just going to use Scikit-Learn. And as you may recall from previous instances, what we have to do is we have to define a model and give it some data, the X and Y blobs that we just said, right? So it's not too hard. We get our model. It's actually quite quick with data of this size. If we had 100,000 data points, this would not be so quick. All right, here's a little helper function that we're going to use just to see what the classifier did. Okay, so down the middle in the solid line, you're going to see the actual decision boundary itself. So that's wx plus b equals 0. Here you see wx plus b equals -1. This is the negative margin where the negative class, the 0 class, the blues begin. Okay, and this is the positive end of things. This is wx plus b equals +1. And this is where the positive class, the orange, begins. Okay. So actually, I probably said that a little bit confusing. I shouldn't have said it that way. Obviously, everything on this side of the decision boundary, everything below, because the weight vector points in this direction, right? This is the positive class. Everything below the solid line is actually going to be predicted as positive. But if any orange dots appeared in between the lower dotted line and the solid line, they would fall inside the hinge losses. The hinge loss has those two components, right? It has the part where there's no loss and we don't try to change the weights. And then it has the part where things are beyond 1, right? And that's where we do change the weights. Anything that's up here, we get some loss. And so therefore, we try to change the weights. So anything that occurs here in between the solid line and one of the dotted lines is in that regime where it's going to try to change the weights. And anything that's outside of the dotted lines towards the bottom or the top, that's in the 0 part, and there's no loss, and there's no attempt to change the weights, okay? So this is where a support vector essentially just tries to find these support vectors, right? These locations right here circled. The circled dots are the support vectors. They are the things closest to the margin in the training set, okay? Those training set elements which lie along the line equal to 1 or the line equal to -1, those are the support vectors, and those are what define how the classifier works. That's why it's called a support vector machine. Everything outside these dots is just BS, and it's ignored by the algorithm. The algorithm doesn't care about these dots, and you can change them around and it won't change the answer, okay? Which turns out to be very useful for generalization. One of the nice things about support vector machines is that a little bit of different random noise in here doesn't really affect stuff, as long as those support vectors are good support vectors for the problem in general. Okay, so again, stuff inside the dotted lines gets some loss, and the machine tries to adjust to make up for that loss, to change the weights to make it happen, okay, to get rid of it. All right, so once we're done with this, we can just see what the actual support vectors are. These are the dots that are circled. They're the points that are important. Okay. Now, as I was just mentioning, right, it's the support vectors that are important. So if you have a slightly different set of data points, you may not have really any change, okay? Here we're subsampling the training set, okay? First in just the first 30 points of the training set, and then here the first 60 and the first 120 points of the training set. And what you can see is there's really no change from 60 to 120 points, even though there's quite a lot of change out here in the blobs. And that's because, again, it's only these support vectors, these closest ones, these dots on the margins, that are the things that define it. Now, with only 30 points, we get a small change, but it's not actually the end of the world. It's still roughly the same kind of decision boundary, okay? So you can see that it's pretty good at generalization in that way. All right, so today you will have watched the lectures about the kernel trick. And the kernel trick, you know, turns out to be kind of familiar to us, even though we weren't using the word kernel trick. Because what is the kernel trick? Well, what we're doing is we're taking the data in some set of variables, and we're going to transform it. We're going to make it higher dimensionality, we're going to add a new dimension onto it. And that new dimension is going to have a nonlinear basis. Okay, it's not going to be a linear combination of those variables. It's going to be a nonlinear combination of those variables. Well, where have we seen that before? Dun, dun, dun. Polynomial features. Oh no. Yes, way back when we were first doing linear regression, we were already doing a kernel transformation. A kernel transformation is just, let's take the variables we've got, we'll make some nonlinear combination of those variables, and we will put it out there for us as a new variable to learn on. Okay, so let's see an example of that. Right, here's a new data set for us to work on. One which is definitely not going to be able to accept a linear boundary, right? We just tried to fit one in this data. So we have the positive classes in a circle and the negative classes in a ring around it. You can't draw one straight line that separates these, because this is what the support vector tried to do when it was trying to fit linear. Instead, if you could fit a circular line around this, then it would separate the two classes, right? So, well, one way you can do this is you can run a radial basis function, okay? A radial basis function is just something that looks like a Gaussian. Now you can use a real Gaussian for this. The real Gaussian is what was done in the lectures, in Andrew's lecture today, okay? You could also just use something that's not actually a Gaussian, but Gaussian-ish, like a parabola or something like that. That's also a possible basis, but let's just go ahead and define it instead of me getting into silly details, okay? So we define an exponential here, and an exponential on x squared gives us something that looks radial basis-y. All right, and we're going to plot in 3D now the original x values that we had, right? There's the original x values, x1 and x2. But now we're going to add r as a third dimension. R is this Gaussian-ish kind of shape to it, okay? So when we put a Gaussian-ish sort of shape in R, and we put that with the center of the Gaussian right where the center of the orange circles are here, right? Then we pull everything up by R, and now it turns out we could draw a line. We can draw a straight plane right in around, let's say, 0.5 or 0.7 or something like that, right? We can draw a cut horizontally. The center of the Gaussian is up here. The ring part is down below, and the support vector, which is a support vector machine, which is a linear in the weights, right? Now can draw a hyperplane through the situation and linearly separate these nonlinear data points, non-linearly separable data points. And that is the kernel trick. The kernel trick expands the dimensionality, and in doing that, stretches it out. Now, let me quickly use the annotation here. Like, for instance, you all remember the XOR, right? If this is the truth table of variable 1, and this is the truth of variable 2, right? And so 0, 0 is a 0, right? And one of the variables true is a 1, but the other one has to be false, right? And this variable true is a truth statement, but if both of them are true, that's not true, right? An exclusive OR says it has to be an OR, but just one of them. This or that, but not both, right? So this is the classic not linearly separable problem, the thing that brought down the perceptron, right? Well, you could do this too, right? We can draw a third dimension now. And we can place our, and we can have the same setup here with x1 and x2, right? But we can bring our truth ones out here in x3 into the z-plane and put our zeros back here on the back plane. And now you can draw a linear separator in between the two of them, okay? So that's a way in which by expanding dimensions, we could also solve the exclusive OR, which is our kind of our prototypical nonlinear decision boundary kind of task. All right. Let's see if I can erase these things in reasonably fast time, not bore you to death. Okay. Brilliant. Back to this. Okay, so let's go ahead and do it. Let's do a support vector which fits this non-linearly separable data and take a look at it. Okay, so here's our decision boundary. Here's the positive boundary, positive margin, and here's the negative margin out here. And you can see where those support vectors are, the ones that intersect those margins. Very pretty. Okay, final extension of the support vector machine. So all of these have been fully separable, right? We can draw some margin in there and have clear space, but lots of data is not clearly separable. Lots of data like this data has no line that we could draw that fully separates the data. Any line we can draw in here, whoops, that was not an annotation. There we go. Any line we can draw in there is going to leave errors on one side or both sides, okay? So what are we going to do? Well, the way in which we handle it mathematically was not really talked about during the lectures fully. I may circle around back to this, but this is not a venue where I can really do that. Suffice it to say that we add in a little bit of slack to the system, where we let it not care so much about things that are just on the other side. And one ways in which we can do that is by adjusting the C parameter. The C parameter is, if you'll remember, the inverse of our lambda parameter when we were doing regularization, with like the L2 norm to squish down the weights, right? C is the inverse of lambda. So when lambda is very, very big, then you're going to do a lot of squishing of the weights, okay? When C is very big, you don't do any squishing of the weights. You let them really, glom on to things, okay? So I think I did that right. Oh, and look, I'm still on drawing. That's why I can't do anything. All right. So here we go. So as I said, when C is large, it exactly fits the margin that's there in the data, which is a tiny, tiny margin here on the left, okay? When C is small, we let it have some slack, and we let the some of these data points be outside the margin, and we're not trying so hard to regularize. I'm now feeling like I have that backwards. Let me think about this for a second. So typically we write, right, when we're doing regular old OLS kinds of things, then we would have 1 over lambda times the 2 norm. Okay. Maybe the 2 norm squared, right? I'm kind of late at night here, and I apologize for messing this up by doing it by memory. But okay, so when lambda is small, this number is big. And that means it takes up a lot of the loss function, right? And the loss function really cares about this. So we really try to minimize it. So when lambda is small, then regularization is big. And since C is equal to 1 over lambda, right? Because we take it to the other side. We move it from what had been the regular fit term, we bring it over to here. Then, so we would multiply through by lambda to make C. And so when lambda is small, C will be small. Oh man, let me say this. You should just ignore what I said for the last 2 minutes, and you should go back and listen to what Andrew said, because he definitely covered this, and I apologize for messing it up here, okay? Because what I'm thinking is that I was totally backwards, because here at the 0.1, C is 0.1, the margin is very, very big, okay? So when the margin is very, very big, we know we care a lot about squishing the weights, right? Because the smaller the weights, the smaller the weights, the bigger the margin. That's direct from the math, because this projection here is divided by this norm. So when this norm is very, very large, then dividing by something large makes very small, and that means a small margin, right? So that is definitely in my head, and I've got that right now. Okay, so double check with the lecture, but I'm almost 100% sure now that this is the part where we really try to push the margin large, right? And that means that happens when C is small. And here is where we don't try to push the margin large, where we let the exact nature of the training set dictate where the margins are, okay? So here we allow more slack in an effort to push the margin large. All right, moving onwards, maybe without all this notation on it. There we go. Okay, so let's use this to actually play and take a look with our penguin data that we saw the last time with logistic regression. Okay, so we have 3 kinds of penguins, the Adelie, chinstrap, and Gentoo species. And we have measurements again, which include body mass, flipper length, bill depth, which is this direction, and bill length, which is that direction. Okay, we're going to use all 4 of those numeric variables and all 3 of those categories, and we're going to fit a support vector machine that's going to try to fit those 3 categories from those 4 numeric variables. Okay. So again, I'm just going to go ahead and straight up use Scikit-Learn and kind of not worry too much about the implementation because it's done for us. But one thing that we do have to do is we have to divide up our data into a training set and a test set, right? We know that we can probably fit the training set very, very well. But if we check our results on a test set, we can get an idea about how well we're going to do to new data that comes from the same process but has never before been seen by the training. Okay, so we don't want to overfit to random noise in our training data. We want to generalize well to new data that comes from a similar process. Well, let's go ahead and do that. So this is the cell which takes our data, takes all 4 variables as the X and the species column as the Y, and splits it up into train and test chunks. And we're going to do 75% for training, and we're going to use 25% of our data assigned randomly to test. Okay. So again, we can control the margin hardness with that C parameter and also with the gamma parameter, right? And as you heard Andrew say, these both control something like the bias variance trade-off too, right? When we make the C value very, very large, we fit exactly that margin and we're exactly fit to the training data, right? We're not going to necessarily generalize well. We might be overfit. We might have quite a lot of variance. Okay, we might be allowing our thing to fit all the wiggles in the data, and some of those wiggles are noise. When we go and that's true also when we have a large gamma, right? No, it's when we have a small gamma. When we have a small gamma, then we can fit exactly to the data. Okay, but when we have a small c or a large gamma, then we are smoothing out over more space. We're letting the margins expand beyond the exact data and getting some slack in them. And when the gamma is large, we smear stuff out with these radial basis functions. And so we are now going to have more bias, but less variance. We're not going to overfit the data. We might possibly underfit the data if we go too far the other way. All right, so let's do this stuff. Let's take a look. When you play, you can try different values of C and gamma. You can see how it looks, how you get different results. But I'm just going to fit one set of data right now, okay? And we can generate these scoring reports where we see precision and recall, for instance, which are measures that tell you about the false positives and false negatives, right? Something which is very, very precise is going to it's not going to give you false negatives, right? Something which has excellent recall is not going to give you false positives. Right here. Thought I had it right here. Let's just do it again. Right? Okay. Something that is precise gets you good true positives, right? Sorry, how many, no, backwards. How many selected items are relevant, right? How many of the things that you've selected are the real deal? Yeah. So we get, if we have very few false positives, then this number is approaching 1, the precision number, right? And recall is how many relevant items are selected, right? So if we don't have any false negatives, then recall is approaching 1. And I think I said that correct earlier. Somebody will double check me. Okay, so we have those kinds of things. Support here just says how many of these classes there are, how many exemplars of the class there are. So there are 40 Adelies and 15 chin straps in our test set data. Okay, and accuracy is exactly what it sounds like. We were 86% accurate on the test set. Okay, now which ones did we confuse, right? We have 3 classes here. Which one did things get confused with? Well, if you look here at the confusion matrix, this is the true label over here. So, and this is what we predicted. So you can see that the Adelies, most of the 40, 34 of the 40, they were correctly labeled as Adelies. But 6 of them were labeled as chinstrap penguins. Okay? And there's some confusion back and forth there, right? So most of the chin straps were correctly labeled chin straps, but a third of them, almost 5 out of 15, were accidentally labeled as Adelies. So Adelies and chin straps are more easy to confuse with each other, and they were never confused with the Gen2s really, except once. Okay? So not only have we used this notebook to get you a little bit of experience with support vector machines, we're using it to remind you about how all these error metrics work for classification. Okay? And I think it's good that you know how those error metrics work, because there is a midterm number 2 coming up in a couple of weeks. Okay? So don't panic. Still caught several weeks, but I just, error metrics, good to know and understand. All right, so that's all I had to show you today. I hope that it made a lot of sense and that you enjoyed everything. Please do come and play with this notebook yourself in Google Colab or your own machine. All right, talk to you later. Bye.